Hi everyone, my name is Kyleigh Quillian and I'll be presenting my falling Slinky lab. This lab looks simple, but it shows something that breaks our intuition in physics. When we drop a Slinky, the bottom doesn't fall right away. Today I'll show you how we measured that using Tracker, how we predicted it using CloseScript, and why physics says this should happen. The goal of this lab was to predict and analyze the motion of a falling Slinky and to compare real movement to a computer model. We used Tracker to record real motion from a video. We used CloseScript to create a computational model. Our guiding question was, does the bottom of the Slinky stay still in both the real experiment and the model? And if it does, why does this happen? What we found is that the bottom does remain stationary briefly, both in the model and in real life, which means it's not a mistake or video glitch, it's real physics. To understand why the bottom doesn't move, we need three ideas. Newton's second law, the motion of an object depends on the net force acting on it. This is how we update velocity and position in our CloseScript model. Drag force. It acts against motion through air. In this lab, it's small, but it helps explain little wiggles or fluctuations we saw in Tracker. Gravitational versus Slinky force. Gravity pulls everything down, but the Slinky is stretched, so it acts like a spring trying to pull upward. When those two forces balance at the bottom, gravity and tension cancel out, which means if there's no net force, there's no acceleration, and the bottom does not move. Observed motion. In our observed motion slide, you can see the data we extracted from Tracker. A Slinky was dropped from 1.75 meters and the bottom point started with zero velocity. When we tracked the position of the Slinky's bottom over time, its motion was almost perfectly flat. At first, the bottom literally just hovers. It doesn't fall until the collapsing wave of tension travels from the top to the bottom. That delay is the reason we see the floating effect. Now, to check if this behavior is just real world randomness or true physics, we built a computational model in CloseScript. Instead of solving one big equation, the program applies Newton's second law, updates momentum and velocity, and then updates position at any time step. This is important because real motion doesn't happen all at once, it unfolds moment by moment. Our model also includes the same forces as in real life: gravity, tension, and drag. Because of that, our simulation predicted exactly what Tracker showed. The bottom of the Slinky stays still at first. In other words, the computer agreed with the real world. When we plotted observed versus predicted motion, the two lines matched closely. There were small fluctuations in observed data that can come from air resistance we didn't perfectly model or slight shaking as the Slinky was released. We also have human error from placing the tracking points manually in Tracker. But overall, both the real Slinky and the simulated Slinky showed the same phenomenon. The bottom remains stationary until tension catches up. So why does the bottom stay still? The bottom feels equal and opposite forces, gravity pulling down and tension pulling up. Until those forces become unbalanced, Newton's second law says there's no acceleration, so the bottom just hangs in place. It only starts falling after the tension wave reaches it, kind of like information traveling through the Slinky. If we added a weight to the bottom, it might still remain stationary, but only if the Slinky is long enough or has a strong enough spring constant to match that extra weight. If the weight is too heavy, tension won't balance gravity and the bottom will fall immediately. So overall, the Slinky experiment shows that forces don't instantly affect an object. Tension has to travel. The bottom floats, not because of magic, but because physics needs time to update. Thank you for listening.